Let's now take a look at multiple variable theorems within Boolean algebra. So let's start with the commutative property. And what this property or theorem says is that the order of a variable in an operation, in an AND or an OR operation, does not influence the result. So we could say that A ORed with B is equal to B ORed with A. And we could prove that by proof by exhaustion, but it's pretty straightforward. If we look at the dual of that, what that is that A ANDed with B is equal to B ANDed with A. Now this seems very simple, but it's very useful when you go to implement circuits and you need to rearrange the inputs into a particular part. So if you had a circuit where you were implementing something where you had an A, B, ANDed together, and this was the schematic, and then you went to a particular part, and the part looked like this with a pin here and a pin here, and this was where A and this was where B was. And you had a connector, for example, where A came in here and B came in here, and, or let's do it like this, B came in here and A came in here, and B came in here, and A came in here, and you were going to route these. You'd notice that this came over to here, and this needed to cross it. So if you were using a single routing layer, you wouldn't be able to do that. But you could easily come back and say, well, you know what, this doesn't matter. I could have drawn this schematic where I had a B on the top and an A on the bottom, and that would have been logically equivalent. So that would have allowed me to come in here and say, okay, I'm going to have, I could have connected this directly to here and this directly to here, and I would have had the same logic. So that's the commutative property, and again, it's used it's commonly used when you look at place and routing algorithms. Okay, so the next multiple variable theorem is the associative property. And a lot of these theorems mirror our decimal algebraic theorem. So the associative property is where you say that the grouping of operations within a logic expression does not influence the result. So property, let's do an example where we said A ORed with B ORed with C. And what we mean by that is that if I group these two together using parentheses, then this is still valid, where we would still be the same as A ORed with B ORed with C, where B and C were grouped together. So we can associate particular variables together with the same operators, and it doesn't influence the result. This is very powerful when we go to look at things like A ORed with B ORed with C ORed with D. That circuit right there would basically be a 4-input OR gate. But if we ever had a fan-in constraint on this, so let's say, for example, we had a fan-in constraint of 2, that just means that there are only 2-input OR gates in my logic family. Well, how do you accomplish this 4-input OR operation if you only have a 2-input OR gate? Well, you could use the associative property and say that I can group these together without changing the truth or the logic of the expression. So what I could do is I could come along and say, I'm going to take A ORed with B as one operation, I'm going to take C ORed with D as one operation, then I'll OR those two results together. So what that would look like is I would go, let's take our original was A, B, C, and D, and then I could break that up, and the schematic would look like A ORed with B, and then I'd have C ORed with D, and then I would OR those two together, and I would have that. So I was able to accomplish it using 3 2-input OR gates, and I was able to accomplish that same logic operation, but I was able to address my fan-in specification. Okay, the dual of this will simply be A ANDed with B ANDed with C, and if I group A and B together, that's the same as if I had A ANDed with B ANDed with C, and I group B and C together. What's also important about these is that this is also equal to A ANDed with B ANDed with C. So whether you don't have the parentheses. And same thing over here, this is the same as A ORed with B ORed with C. So that's part of the proof, but typically not drawn like that. So that's the associative property. And next let's take a look at the distributive property. And the distributive property says that an operation will distribute through a parentheses. So let's take a look at that. So this is the distributive distributive property. And what this says is that if I had A ANDed with B ORed with C, I can distribute that AND operation through. So I can take A ANDed with B ORed with A ANDed with C. So it distributes through. So I can go A ANDed with B ORed with A ANDed with C. So that's the truth of this theorem. Now this becomes useful. Let's write the dual down, and then we'll talk about the usefulness of this. So I have the dual right here, where I'm going to have A ORed with B ANDed with C. So that's equal to A ORed with B, distribute it through, ANDed with A ORed with C. So A ANDed with B, so A ORed with B, ANDed with A ORed with C. So it distributes through. So you say, well, how is this of any interest to us? So what we could do with this is, let's say, for example, we had this expression right here, where I had A, B ANDed together, and then I had A, C ANDed together, and those were OR together. So I had some logic expression like this. And I came along and I noticed that A was common to both of these product terms. Well, I could use the distributive property to say, okay, you know what? This is actually going to be the same as if I took this, and I took B ORed with C, and then I took that whole thing and I ANDed it with A. So I could actually get rid of a gate by recognizing that. So this is used in a lot of logic minimization, the distributive property. Okay, so let's also take a look at the next one, which is going to be called absorption. So the absorption theorem says that if a variable, if a logic expression, when a term within a logic expression produces the same outputs as another term, the second term can be removed without affecting the result. Okay, so that's the textbook definition of this. So what does that really mean? It means if I had A ORed with A ANDed with B, if you think about it, I have two terms, and they both will produce the same result. So A will produce whatever A is, but this one right here will produce some results, but since it's ORed with this, the A will always override it. So what you can say is that this term is not necessarily needed, because even though it produces some results, when it's ORed with A itself, because it had A within it, when it's ORed with A will always win out. So, so what this means is that we can reduce that or eliminate that term and say that it's absorbed into this term right here. So that's absorption. And this allows us to minimize logic a little bit, minimize logic. So let's take a look at, this is absorption. That's an N right there. Let's take a look at the dual. The dual of that would say that A ANDed with A ORed with B is also equal to A. So one of the terms was absorbed into the other one. Okay? All right. So now let's take a look at yet another multiple variable theorem. And in this one, what we are going to have is we will have the theorem called uniting. And uniting means that when a variable and its complement appear in multiple product terms within a common variable, then within a logical OR operation, the variable B does not have any effect on the result and can be removed. So what does that mean? What that means is that I have A ANDed with B, ORed with A ANDed with B not, and that's equal to A. So I have a variable, B, and I have its complement, B naught, and they're both ANDed with a common variable, which is A. Okay, so I have the situation where A is in both terms, and it's an AND operation, and notice that A is ANDed with B, and also A is ANDed with B naught, and these are ORed together. So what this means is that B does not have any impact on the result. So in this situation, you can think about it, A and B, or B is always going to either be in these terms either a 0 or a 1. So one of these terms will survive, and the other one will simply go to 0. It'll either be this one or this one, depending on the values. And so B does not have any impact on this, so you can actually remove it from the expression. So that's the uniting. So unite these together to eliminate the B variable, which doesn't have any impact on the output. The dual of this is going to be A ORed with B ANDed with A ORed with B naught. And what that says is that now you have the same thing where B and B naught are both ORed with the common variable, which in this example is A. They're ANDed together. B does not have any impact on this logic expression. So you can simply remove it and you're left with A. Okay, so that takes care of 5 variables, or that takes care of, let's see, that takes care of the identity theorem, or no, not the identity. That takes care of the involution, excuse me, not involution, commutative, associative, distributive, absorption, and uniting. So that's 5 of the first single variable expressions. The 6th, and a very powerful one, they're all very powerful, but the 6th Boolean algebraic theorem is De Morgan's second law. So this is where we finally come back to De Morgan, and this is just simply called De Morgan's theorem. Now remember, De Morgan contributed 2 theorems. He had duality, and then he had this one that we're talking about right now. Whenever you talk about duality, you just say De Morgan's theorem of duality. For this one, you just say De Morgan's theorem. So De Morgan's theorem by itself is the name of this second theorem. Okay, so here's what De Morgan's theorem says. It says that if you have an OR operation where both input variables are complemented, so I'm going to complement both of them, then that is equal to an AND operation of the original variables with the output complemented. Okay? Now graphically, it's a little easier to see that graphically. What you're saying there is that if you have A and B, and they come into inverters before going into an OR, then that is the same as A and B ANDed together with the output inverted. So you can say this, that any OR gate with its inputs inverted is equal to an AND gate with its output inverted. This is very interesting because if I draw these inverters as inversion bubbles, you could draw this equivalently as this. So I had an inversion bubble, boom, boom. And then over here what that's going to be equal to is simply an AND gate with its output inverted. So notice that this is a NAND gate right here. So this is a very powerful theorem because it allows us to convert any logic expression into something that is implemented with NAND gates. And NAND gates, as we've seen before, are very important because they are directly implementable in CMOS. So this is a logic manipulation that's very common in order to get logic expressions in a form that can be directly implemented with CMOS technology. Let's take a look at the dual of this. So the dual is going to be if you have an AND operation where the input variables to the AND operation are inverted, it's going to result in an OR operation of the same 2 input variables with the output inverted. So if I draw that graphically, that looks like this. A and B, if I'm going into an AND operation where the input variables are inverted, then that is equivalent to A and B going into simply an OR operation with the output inverted. So notice again here that I was able to convert this into something that looks like a CMOS gate, which is the NOR operation. So that is De Morgan's theorem. Now let's look at a practical application of De Morgan's theorem. We talked about Boolean algebra only has 3 operations, ANDs, ORs, and inverts. So let's take an example of, let's go with De Morgan's example. So let's say that you had a logic expression that was synthesized using Boolean algebra, and you had something that looked like this, where you had A and B going into an AND gate, and then you had C and D going into an AND gate, and then both of those were going into an OR gate. And you said, okay, I want to implement that, but I want to do it in gates that can be directly implementable with CMOS. So you notice that ANDs and ORs are not directly implemented with CMOS. So can we manipulate this? Well, it turns out that with everything that we have, we can do that. We want to convert these into NAND gates and OR gates and optionally inverters if necessary. But how do we go about doing this? Well, it turns out that we can use a couple of the theorems. We can actually put double inverters anywhere that we want using the theorem that we covered before, the single variable theorem, which means that it was the involution theorem. We can basically go to any wire and we can insert double inverters, and it does not change the logic. So if I drew this, what I'm going to do, one of the shorthand ways to do inverters is simply with an inversion bubble. So I could have drawn that as an inversion bubble and inversion bubble. So we call this the double bubble. So what I could do is I can come in here and I can put inverters anywhere on this net as long as I put two at a time. So what would happen if I came along and I put an inverter there and an inverter there? I have not changed the logic functionality of this at all. So I could come up here and do the same thing. I still have the same logic expression, except I've done something very important. Number one, I've converted these into NAND gates, and number two, I've converted this into an OR operation with its inputs inverted. I then use De Morgan's to convert that into an AND operation with its output inverted. So this can be, anytime I see one of these, what we call a sum of products, where I have an OR gate that's fed by two product terms or multiple product terms, it's called a sum products. And I can come in here and I can directly convert this into NAND gates by first performing a double bubble using the involution theorem, and then I can, on these internal nets, and then I have inherently converted the product terms into NAND gates, and then I use De Morgan's to flip the sum term into a NAND gate also. So this directly goes to A, B, NANDed together, C and D NANDed together, and then the entire thing NANDed together. So that's a very practical application of De Morgan's. Same thing we can use when we have a what we call a product of sums form. So let's say I had A and B that were summed together, and I had C and D that were summed together, and I took those and I went into a product term. So this is a product of sums expression. And I want to convert that into something that can be directly synthesized with or directly implemented with CMOS. So let's do involution, and we'll put double bubbles on these nets right here. I haven't changed the logic functionality, but I have changed these to NOR gates. And then I have changed this to an AND gate with its inputs inverted, which I can, via De Morgan's, change to an OR operation with its outputs inverted. So this then goes directly to an implementation using only NOR gates. So I've got A, B, C, and D, and then A and B are NORed, C and D are NORed, and then those outputs are NORed together also. So this is now directly implementable with CMOS. So this is a practical application of De Morgan's. One final thing on De Morgan's is that there's a algebraic way that De Morgan's is implemented, and it's called the breaking the bar and flipping the operator. So let's take a look at that, because this is commonly used in when you manipulate manipulate logic expressions algebraically. So the rule is the break the bar, flip the sign. And what that means is that if you ever have a logic expression such as A ANDed with B and it's inverted, the whole thing's inverted, I can come along and I will have a true logic expression if I break the inversion bar wherever there's an operator, as long as I change that operator. So I need to change that from an AND to an OR. If it was an OR, I would change it to an AND. So that's like saying that that's the same as saying A not ORed with B not. So this is the algebraic form of this. If you think about it, what I have here is I had A and B ANDed together and then inverted. So that's what that logic expression looks like. This right here, I have A and B inverted prior to going into an OR operation. So you can see that this is simply De Morgan's. This is just another way of viewing De Morgan's. Same thing that if I had an operation like A ORed with B inverted, I can break that bar, and it stays true as long as I change that sign to the opposite. So if it's an or, I change it to an and goes to or. So in this situation, this is the equivalent as saying A naught ANDed with B naught. Those are true. So let's take a look at it. This one right here is drawn where I had A, B, ORed together, and then their output was inverted. This one was drawn where I had A and B inverted prior to going into an AND operation. And so you can see that's De Morgan's also right there. Now what's really neat about this is you can introduce double inversions algebraically by simply putting two bars together. So if I had, for example, let's say I just had F is equal to A ORed with B, and I wanted to change that into something that used NAND gates and NOR gates. What I can do is I can always double invert something without changing its logic. So I can always do that. That didn't change anything. I just complemented the output twice. But I did now introduce a bar that I can break. So now what I'm going to do is I'm going to break this bar, and it will remain true as long as I change that sign to an AND. So I can rewrite this as, still have the top inversion bar, but I'm going to have A naught ANDed with B naught. Okay? So this expression now is still true, and you notice that I have, this is actually a different form of the expression. Okay, so that's De Morgan's algebraically, and that summarizes the multiple variable theorems. So if I was to look at the entire summary of Boolean algebra and kind of look at the single variable theorems and the multiple variable theorems, you can kind of see them right here. So we had single variable theorems, identity, null element, idempotency, complements, and involution, and you can see the original and dual. And then we have commutative, associative, distributive, absorption, uniting, and then finally De Morgan's. Notice that De Morgan's theorem of duality is not listed because it's implied in the way that you list this table out. So the dual over here, that represents Morgan's theorem of duality. So in reality, there is 12 theorems that we covered that are in this table, but the 12th, or the first one, duality, is listed over here. So those serve as the framework for Boolean algebra, and they allow us to do things such as synthesize, minimize, and manipulate logic expressions to make circuits more implementable.